All right. So, uh, starting out, I have kind of time to look at the exam grades. Obviously, there's still 20 points missing. I'll kind of make, kind of tell you what the average is and everything after I get those graded. I'll spend a lot of time today and tomorrow. I should be able to get near the first section. So, we'll get graded first. So, I should have yours done before we meet on class Friday. So, I'll talk a little bit more about it on Friday once I have kind of everything graded. I can kind of see where all the scores lie. Question 7, a couple of you emailed me, and if I tried to email you back if I sent you a wrong response first. Yours was showing up different. I don't know how it happened because honestly, I was kind of using the same questions for both sections, but when I copied it over, one of yours on question 7 had a duplicate answer, and for the other class, it had a duplicate answer, but it was the wrong answer. And so I was like, if someone emailed me, I was saying, well, yeah, it's the wrong answer. So on yours, there was 2 answers that were correct. So I went back through this morning and kind of regraded that so that if you selected either one of those, it was counted as correct. Okay, so if you take a look at your exam grade, if you missed number 7, potentially you actually now have credit for it because there was actually 2 correct answers. Other than that, didn't have too many issues. There's a couple, I think must have been some maintenance on Canvas because there was about a half-hour time block where a lot of you were having kind of trouble uploading things, that short answer question. But I got a lot of emails right after the exam, which was kind of what I mentioned. So thanks for, I'm glad that kind of went okay. Other than that, I kind of have the next set of slides up there on Canvas. So I'm calling it week 13. We're going to go through some more hypothesis testing, right? So it's kind of this week and then next week, we'll be doing some different types of examples with confidence intervals and hypothesis testing again. We're kind of pushing it a step further, which is something you'll see in a lot of different courses, potentially upper level courses called t-tests. We're looking at the differences in means between 2 groups, right? So I'll assign after class today a Connect homework and an Excel assignment. We by no means have went over near enough stuff for you to complete all of them, but they'll be up there so that as we work through material, you can kind of knock out a couple questions on each one of those as we kind of progress through this new material, right? I'm guessing we'll probably have covered everything by Monday where you could get kind of through the entire thing. If not by next Monday, definitely by next Wednesday, right? And then we'll have that Friday, we'll start kind of some linear regression stuff before we go to Thanksgiving break. And then I'll kind of, those last 2 weeks before exam week, kind of while we're not meeting in person, we'll go through some more linear regression stuff. I'll probably keep the format the same. If you want to get on the Zoom call and watch the live kind of me recording these lectures with no one in the room, you can do that, but I'll be posting them kind of every time like I typically would, right? The format kind of just won't change those 2 weeks. It's just, for those of you who are in person here, you only have the Zoom or the kind of the YouTube, right? And I might set up some additional times as we get kind of close to that final exam week, or if you want to have like a review session, you guys can kind of Zoom in and ask me questions and kind of go over some of the practice exams I'll put up for that, okay? So that's kind of where we're going. Like I said, I'll talk a little bit more about the exam once I have kind of all of them graded on Friday, right? So hopefully maybe some of what we do today will kind of make, some of the mistakes that were made on the exam make a little bit more sense, since we're going to keep doing confidence intervals and hypothesis testing. So we're going to build confidence intervals for 3 different situations, where now instead of 1, we have 2 populations, right? So same 3 situations and the same kind of principles apply. When we we know the population variance, or we're dealing with proportions from 2 populations, we still use the standard normal distribution. And when we deal with 2 sample means from 2 different populations, but we don't know the population variances, all we have is sample variances, we're going to keep using the student t-distribution. So a lot of this, won't be a whole lot of new information. It's just applying what we already had to something where we can make some more interesting statements. We can do the same thing for hypothesis testing. We're going to have the same 3 types of tests. Yeah. Okay, let's double check on this. Maybe I put it in the wrong section. Files, lecture slides. Should be down here. They're not showing up?
Not for me. Sorry, maybe it's
okay.
Sorry.
Okay, maybe refresh. It's okay. Let's hold off on questions. I mean, unless you have specific problem, or if you do have a specific problem, maybe email me about that. Otherwise, like I said, when I'm done grading them, I'll talk a little more about the scores on Friday. So let's hold off on the discussion for that. If you do have individual questions on individual questions, email me or set up a time we can kind of meet and talk about those. Okay. Where was I? Okay. So we've got these different types of, or these kind of scenarios that we're a little bit familiar with, but now it's just going to be for two populations. And then we're eventually going to be doing one called matched pairs. Well, this will be a little bit different than anything we've done before. Okay? So kind of, we have three motivating examples. So maybe we're looking at the difference in starting salaries between different majors in college. So we could look at what the average for each of those groups are. If we had the known population variances, we could start to build confidence intervals for what the true difference is between econ and kind of theater majors starting salaries, which I have here. Right? If we had proportions, right? Maybe I have two different time periods, 2010 and 2011, and I say, okay, how were what were the views on affordable health care, and did they change over those two time periods, right? From 2010 to 2011. I could build a confidence interval for what that change in the proportion was. Right? If I had maybe people who are texting and not texting while driving, I have the average response times. I could look at what's the true kind of difference between response times of people who are texting while driving and not texting while driving. So those are kind of our three motivating examples, and we'll kind of build confidence intervals and do some hypothesis testing for those examples, right? So the first one is where we're comparing two population means, and we know the population variances. Right? So for each population, they're going to have their own population mean. Now, we usually can't observe this. That's why we're going to have to maybe build a confidence interval. And they're going to have their own population variance. They'll also have its own sample size. Okay? And if we take that sample, we'll have a sample mean for that group. In the second population, it's going to have all the same things, right? There will be a population mean for that second group. There's going to be a population variance. And if we took a sample of size N2, which is just the sample size from group 2, we could calculate a sample mean for that group. So if we think about the difference between these two sample means, it's going to follow similar to what we were doing before. So I'll come back to this in a second because I think it can make this make a little more sense. So before, what we were doing was we said, all right, we have this distribution of sample means. It's going to be centered around whatever the true population mean is. Right? Kind of the variance of those sample means was the original variance of the data divided by our sample size. Now, try to give you, well, first we'll do this. So what's going to be true, I'll tell you what is true, and then I'll try to show you why. So if I think about, if I'm looking for the difference in two groups' sample means. So the statistic that I'm now interested in is not the sample mean, right? The statistic I'm interested in is the difference in sample mean. So it's almost like, here's the statistic I'm interested in. What ends up being true is that difference will be normally distributed, and it's not going to be centered around a population mean now, but it's going to be centered around the population difference. So it'd be centered around whatever the true difference was. Now, I usually can't observe this. All I can observe is the difference between my sample means, right? So, we're going to have to, we can only observe sample means. But we're going to have to do things like hypothesis testing, build confidence intervals to try to narrow down where exactly is this true difference. What ends up being true is the variance for the difference in my sample means is simply what the variance for each one of these sample means would be added together. So, right, that's what we had here, but now it's from group 1 and add in the variance from group 2. Okay? Now, if I want the standard deviation, all I have to do, take the square root of this, right? So I think I have that in the slides, where if I want the standard deviation, I would take the square root of both of these things. But really what this comes from is the variance is simply adding up the variance of each of the sample means that you're trying to find the difference between, okay? So I think the motivating example I had that we'll eventually get to was kind of maybe this is the difference between econ majors and theater majors. Okay? Does that kind of make sense? All right. So I'm going to jump the gun a little bit here, but just stay with me. So before, this is how we built our confidence interval, right? So we look at the statistic we're interested in, we go a certain number of standard deviations away, and whether or not we use the student t or the standard normal depended on the type of example we had. We knew the population variance, we used the z distribution. I then multiplied by, and this represented the standard deviation of my sample means, so just taking the square root of that. So now if I want to build a confidence interval, what am I going to build it around? Not the sample mean, but the difference in my sample means. So almost think about it like this. If I knew the population variances, I'm still going to go a certain number of standard deviations away. And how many standard deviations? Well, I'm going to use that standard normal distribution to get that. And then here, I won't multiply by this, if this is the number of standard deviations away I want to go above and below to get my lower and upper bound, that's why I was multiplying it by the standard deviation, right? It would be 2 times the standard deviation, 2 standard deviations away. So I'm still going to be multiplying by a standard deviation here. It's just now it's the standard deviation for the difference in my sample means, because that's the statistic I'm looking at. If I have the variance, I know the standard deviation would just be this, and take the square root. So times the square root of each group's sample variance divided by that group's sample size. Okay? So it's the same kind of format we were doing before. It's just we have a couple moving, more moving parts now because we're looking for the difference between 2 groups as opposed to just focusing on one group. Okay? So why do I know this is normally distributed, and why do I know that kind of this will hold? Right? It's a little bit harder to give you some intuition behind kind of the variance, but you can kind of imagine if I have 2 different samples, I'm going to have different, they each have their own variance. The total variance, when I look for the difference between them, would just be add those variances up. Right? It's a little bit hard to give you a visual kind of intuition behind that, but I think I can give you a pretty good visual intuition behind why the difference in my sample means will be centered around whatever that true population mean is. Okay? So, am I okay to erase this stuff right here? Okay. So, let's assume that I'm thinking about sample means here. So let's say, here's group 1, right? I know that the sample mean distribution for group 1 will be centered around wherever the true population mean is. I also know for group 2, their distribution of sample means would be centered around whatever their population mean was. So if I'm looking for the difference between the two, what's the most likely outcome I see? Well, remember, this y-axis, these distributions are really trying to give us kind of an idea about what values are most likely for C, or the higher probabilities. So what values have the higher probabilities of me seeing as a sample mean in this first distribution? Would be values that are right around that population mean. In fact, the most likely outcome, right, is whatever that population mean is. Same kind of thing here. So if the most likely difference for me to see would kind of be whatever that difference is between the two. Right? And then you kind of think about that here's the next most likely outcomes. So now the next most likely differences for me to see start to kind of fall, and you kind of end up, and it wouldn't, I'm drawing this, if I think about the difference, it might actually be like way over here, but these are the next most likely outcomes. It's not very likely for me to see kind of differences here or differences that are way out here. And so because I know that the 2 sample means are normally distributed, you kind of see the intuition behind, okay, this will be the most likely outcome for me to see, which would be the true difference between my population means. And then kind of the next most likely difference for me to see might be, the difference between here and here, or the difference between here and here. Now you can kind of map that out into this new distribution, which will be normally distributed around the most likely outcome, which is the true difference between these means. Right? And so that's kind of why, that's kind of a decent visual. It's probably not not doing things theoretically kind of correct here, but I think that gives a pretty good intuition behind why. Okay? But we do know theoretically for sure that that difference in our sample means will be normally distributed around whatever that true population difference is. Okay? Any questions on that? Okay, so we had that confidence interval equation. We said it really is similar to what we were doing before. It's just we have a couple more moving parts. So, I think I showed, yep, right here. And actually, if you have this open, if it's easier for you to see this, let's make that, I don't know why I had this smaller, because now we can see this is all on one line, okay? So, we've got our confidence interval equation, right? This was just, well now maybe that's why, because I didn't want to move these around. Right now, this is just like my sample mean was before, and this is just like my variance before, right? I kind of had that work up on the board already. So, what are our steps? Well, now we have to identify a few more pieces of information, right? We need the sample sizes, the sample means, and the population variances from both groups. For building a confidence interval, we have to go back and remember, right? We could build several different confidence levels corresponding to several different alpha values. So we have to identify what alpha we want. We still have alpha over 2 on either side of our interval, right? We'll find the z-score that gives us alpha over 2 on each side of our interval. But at that point, now that we know this is the equation for kind of the difference in population, sorry, the difference in sample means, we're trying to build a confidence interval for the true difference in population means, now it's a matter of plugging and chugging. Right? So let's go back to that example when we're thinking about econ and theater majors, right? So if I find that, econ major starting salary is $45,000 from a sample size of 40, I sample 50 theater majors, find an average kind of salary for them of $33,000, and I somehow know the population variances, right? So I just kind of listed, those are the 6 things that I needed. But if I want a 95% confidence interval, what's my alpha value? 0.05, but the value that I'll look up on the table is 0.05 or alpha divided by 2, so 0.025, right? So I want to find kind of the z value that gives me 0.025 in each tail, right? So if I go open up my z table, right? Rotate this, I want to find 0.025, so I see what's the closest value. Well, this is a nice one because it's actually exactly here. So negative 1.96, right? So I plug in that 1.96, right? Now, when I looked it up in the table, I found the negative, but kind of remember, if we look here, I go back, right? The positive and negative sign are already kind of built into our equation. So the negative 1.96 would give me my lower bound. Positive 1.96 would give me my upper bound. Just a matter of plugging our values in at this point. We kind of get this nice kind of narrow confidence interval, right? So what I can say when I can build these confidence intervals now for the difference in groups, and this one, I think I might have actually just, I don't actually know the true population variance, so I just plug a number in there. And I probably should have chosen a higher number to make this a little more interesting an example, but it gives us something we can kind of talk about. So if this was the true confidence interval, right, based off the sample evidence I found, what I could say is, what, it was something like, I don't know, 11,912. These aren't the exact numbers, but for what I'm going to say, it'll be fine, right? So here is my kind of confidence interval, right? Here's my lower bound, here's my upper bound. So I know that the true difference is somewhere in between those values. Right? So what I can say is the true difference between kind of econ and theater majors starting salary is somewhere in this range of values. So I can say with 95% certainty, it's definitely a positive value, which would mean if this is positive, that the econ majors would have a higher starting salary. And I could even say with 95% confidence that it's somewhere above 11,900 and somewhere below 12,000. So that's, that would be a pretty useful thing to kind of tell someone if you're kind of comparing the difference in starting salaries and between majors. You could build these different confidence intervals and tell you how much more you could expect. Now, let's say we had found like a difference that was a little bit closer, right? So let's say instead, I go out and take some samples, and maybe when I build my lower and upper bound now, I don't know, I see something like this, right? Well, now, with 95% certainty, I can't really say which of these majors makes more, right? Because it could be that this is positive. Well, if this difference is positive, that means econ majors would be making more. But it could be that it was negative, right, somewhere over here, which would mean that theater majors would be making more. Or it could be 0, which would mean that the starting salaries are, the only way that this difference equals 0 is if the starting salaries are the same, right? So when I had a confidence interval that kind of crossed over that 0 threshold, similar to before, we really can't make any useful statements. But if all those values fall on kind of one side, now we actually can kind of say something that actually has some relevancy, right? That we could actually start to make decisions based on, at least at the 95% level in this for this example. Okay, so let's go through another example with some different values and just kind of think about just seeing more repetition of how we do this, right? So let's say we think Indiana is a better state than Ohio, and so we go out, we get some crime data, 24 years for both states. So the sample size here is going to be 24 for both groups, right? 24 for Indiana, 24 years for Ohio. We find the robbery rate in Indiana was 109 out of 100,000 people, and Ohio was 163 out of 100,000 people. Right? So we'll use that 109 and that 163, right? We want to build a 95% confidence interval for the true difference in Indiana and Ohio crime rates. We somehow have the population variance. Maybe this is from like previous historical data. So we've got a population variance for Indiana of 175 and a population variance for Ohio of 497. Well, first of all, if I'm thinking about the difference between Indiana and Ohio, right? If I took the sample mean I found from Indiana, subtracted the sample mean I see from Ohio, 109 minus 163, minus 163, so what? Negative 54, if I'm doing math in my head correct here. So what I know is this was the sample difference that I found. I'm then going to build my confidence interval around that. Right? So I know that negative 54 has to be smack dab in the middle of my confidence interval. Whatever that sample difference is I found, that's what my confidence interval is being built around. So if I look here, what answers could I rule out right away? Is negative 54 in this range? No, not even close. I think if we look at the rest of these, I think it splits all of them kind of in the middle, or at least it looks pretty close. I'd have to kind of do some, nothing looks completely off, right? But we can at least kind of rule out this one, right? Because we know that our confidence interval has to be centered around whatever that sample difference we found was. At that point, it's just a matter of, look, we were given the sample sizes, population variances, and sample means. If we wanted to build a, what was it? 95% confidence interval, based off what we did in the previous problem, what do I know that Z value I'm going to look up has to be? 1.96, right? When we're building these confidence intervals using that standard normal distribution, you should be pretty much using the same Z values all the time, right? I'm not giving you weird alphas. I'm giving you the same kind of 3 benchmark, 99, 95, 90% levels. So anytime I want a confidence interval of the 95% level, when I'm using the standard normal distribution, it's always going to be 1.96, right? So I know it's 1.96, kind of from my previous work and how we looked it up on the table. At that point, it's just a matter of plugging and chugging, right? Plugging those numbers in, right, and getting our lower and upper bound. Okay? So, the key, kind of similar to the last exam, once we work through a lot of these, is going to be identifying the correct equations. But, if we have 2 different groups and we're looking for the difference in their means, and we know the population variances, should be, we're using this equation. Right? Our group 1 was Indiana, our group 2 is Ohio. Okay? So this is kind of an interesting confidence interval in that, what could I say at the 95% level here? 95% certainty, remember these were robbery rates, I could say that Indiana, what? If these are all negative, so I'm saying with 95% confidence, the true difference is somewhere in this range, and they're all negative values. So with 95% certainty, I could say that Indiana has lower robbery rates, right? Because the only way that the true population, right? You think about it this way. If all the values I saw in this range were negative, the only way I have negative values is if Indiana has lower robbery rates. So with 95% certainty, I could say that Indiana has lower robbery rates. I could even take it a step further. I could say they have somewhere between 43 and 64 fewer kind of robberies per 100,000 people. So, this two population stuff, these confidence intervals, we start to have a lot more power with what we can say, right? I thought this was kind of a fun example. Those were the actual robbery rates too. I just couldn't really find great population variances there, but kind of interesting to think about, these types of examples that we could, whatever you're interested in, you could do this, right? To find the difference between two groups. Okay, so now we're going to introduce kind of hypothesis testing, which is a little bit different, but it's really still pretty much the same thing we were doing before. So we're going to call the difference between the two means capital D. So this represents kind of the true difference between the population means. Kind of just prevents us from having to write as much out. So we're going to assume that the difference is some value, right? What we're going to do for all the examples in this class, outside of me probably showing you a little bit in Excel what happens if we don't use it, because in practice we could assume that the true difference is any value we want, right? But often we're going to use 0. And in this class, any exam question I'm going to give you, or kind of anything that we're doing on homeworks, you'll always kind of be using this assumed true difference of 0 when we're looking at the difference between two groups means. Okay? So we're going to have a right tail, a left tail, and a two-tailed test, right? Just like we did before. I mean, this is really the same thing we were doing before, except for instead of a one mean, we have kind of the true difference in means. And then we assume that difference is a certain value, which we said in our case, D subscript 0 is always going to be the value of 0. So why am I always going to choose the value of 0? Well, if we use this Indiana, Ohio kind of idea, if I, maybe I have the assumed true difference is 0 and I have a left-tailed test, right? So maybe I'm thinking about my alternative hypothesis is this. What this is really saying, right, is the true difference less than 0, which if I kind of rearrange this a little bit, I can see what that's really saying is Indiana's robbery rates lower than Ohio's? Right? So that's why we typically, 0 is a very common assumed true difference to use, because what you're really saying is, well, I want to test for whether or not Indiana has lower robbery rates than Ohio. If they have lower robbery rates, and I rearrange that, what I'm really saying is that true difference less than 0. Maybe I want to test for whether or not Indiana has higher robbery rates. So if this is difference would be positive, right? If the difference is positive and I rearrange it, what I'm really saying is, does Indiana have higher robbery rates than Ohio? And then of course I could do simply, are they not equal to each other, right? Which, if you're saying that the difference is not equal to 0, what that's really saying is these are just have to be different values, because the only way that this isn't equal to 0 is if those two means are something other than each other, right, or they're different from each other. So, once we have this written out like this, honestly, hypothesis testing becomes a little bit easier in the sense that we're always going to be using this 0 value. We don't have to worry about this assumed true value. So when we're thinking about the distribution of our difference in sample means, well, remember, once we don't know what the population, if we don't know what the population means are, we have to center it around some assumed true difference between the population means. Well, we're always going to be using 0. So for hypothesis testing, for two population examples, our kind of distribution of that difference in sample means will always be centered around that assumed true value of 0. Okay. Any questions on that? Okay with that? So, I want to do this right here, see if we can kind of figure out what that test statistic would be. So before, all right, here was my test statistical equation when I knew the population variance, right? Where this denominator represented the standard deviation of my sample means. So now if I want to find the test statistic for the difference in sample means, well, I'm no longer using just a sample mean. I'm going to be using the difference in my sample means. I'm then going to subtract not the assumed true mean, but the assumed true difference, which for us, we said we're always going to use 0. So essentially, we could just ignore that, right? Subtracting 0 doesn't do anything. So if you want to, it is floating around there, but in practice, right, if we're using 0, it just kind of goes away. What we're then going to divide by is the standard deviation of the statistic we're interested in. So before, right, standard deviation of our sample mean, now it's going to be the standard deviation of the difference in our sample means, which we had earlier for confidence intervals was just the square root of each group's population variance divided by that group's sample size. So it's really following the same format as what we were doing before. Like I said, similar with confidence intervals, there's a few more moving parts now, okay? So one thing to kind of point out here is because I'm always using that assumed true difference of 0, if this denominator is a standard deviation, it always has to be positive, right? Variances and standard deviations are always positive. So if I'm using this assumed true difference of 0, ignore it. Whatever difference I find in the sample means, it tells me the sign of my test statistic. If I find a positive difference divided by a positive value, my test statistic will be positive. If I find a negative difference, the difference is negative, divided by a positive value, then my test statistic will be negative. Right? So that makes it a little bit easier than what we were doing before with one population because we're always going to be using that assumed true difference of 0. Okay? The steps are all going to be the same. I mean, this is literally the exact same steps. So I think here I've got, looks like the critical value approach. We could do the p-value approach as well. I mean, everything's going to look the same. This is literally a slide kind of that we had before, where basically now instead of means and assumed true means, you would just put in the difference in the assumed true difference, right? So the way we find p-values, exactly the same as what we did before. Like once we get our test statistic for these two population examples, hypothesis testing is no different than before. Once we have our test statistic, we can look up our p-value, or we could plot that test statistic against the critical values. But the actual process doesn't change at all, okay? Other than, this test statistic, right? And that's what I had up there on the board. Now, another thing you could think of is this difference in sample means. You can kind of think about this as like your sample difference that you found. I might even say that kind of in my language sometimes. And then we use that assumed true difference quite often, for all our examples of 0, right? And then I think I had the slide here. The critical values are the exact same as well, right? Because we're still using that standard normal distribution. Nothing else changes here, okay? Where are we at in time? Oh, okay. So let's say we want to find the true difference for whether or not tropical storms have increased in recent years. So I don't have the most recent years, but I do kind of have a newer time period and an older time period. Let's say if we were to look at all of kind of the historical data that we have, I don't know, somehow we know the population variances here, right? This isn't probably the most likely outcome, but we're starting out with these examples where we know the population variance. Once we understand that, we'll kind of move to when we only have a sample variance. So let's assume I know the population variance for tropical storms during this time period, and I know the true population variance for the number of storms kind of in this time period, right? I find that per year, the average tropical storms in the newer time period was 15.5, and the average kind of number of tropical storms per year in the older time period was 9.7. I've got the number of years, so that's kind of like my sample size from these two groups. And I'll kind of say, define the difference as group 1, which I've indicated is the newer time period, minus group 2, which is the older time period. Anytime we're looking for differences in time periods, it's safe to bet you're always going to have that kind of newer year as your group 1, and that older kind of time period as your group 2. Because it just kind of makes sense, right? If I'm wondering whether or not tropical storms have increased, all right, what I'm really thinking about is that mean from kind of the newer time period? I think it ended in 2011, and I think the other one ended in 89. If I want to know have they increased, I'm saying, okay, is the newer time period minus the older time period greater than 0? So kind of using that newer time period just kind of lines up with how we would typically say things in English. Have they increased in recent years? You wouldn't, if I set this up where I looked for the difference between the older and the newer time period, I'd be like, if I look backward in time, was the number of tropical storms higher? Like it's just more convoluted in English. So this is, typically you'll always have kind of the newer time period first. Right? Well, if we want to know whether or not they've increased, this is what we have. What we're really saying is, okay, I want to test for whether or not this true difference, D, is greater than 0. Right? So that's my alternative hypothesis. That's what I'm wanting to test for. Right? So if that's my alternative hypothesis, what is my null? Well, that would just be that the difference is what? Yeah, less than or equal to 0. So I've got what type of tail test here? Greater than sign, so right tail. Yep. Greater than or right tail, I guess, test. So greater than 0 in the alternative, so we assume the opposite was true, kind of stack the deck against ourselves. Now, I already mentioned in an example like this, I'm always going to use that assumed true difference of 0. So don't ever think of there should be any other values kind of in here. Okay? So once I know I have a right tail test, how can I find the critical value? Maybe at the 5% level. Right? When I'm finding a critical value, what I'm really saying is, okay, what's the cutoff such that if I see sample evidence that translates to a test statistic, remember, we have population variances, so we're using that Z distribution. What's the critical value such that the probability, if I see a test statistic any further away from that assumed true difference, the probability would have to be less than an alpha, right? When I'm choosing that critical value, it's really because I've chosen alpha, right? So if I want 0.05 in this right tail here, kind of thinking about this is my rejection region once I find that critical value. Well, first of all, I know it has to be what? For right tail test, critical values are always positive, right? Because this distribution is centered around 0, so anything on the right is going to be a positive value. So I go to my table. I want 0.05 in that upper right tail. Right away, I know it has to be either A or C, because those are the only positive values here. Well, you can see it's already C, but now if I want 0.1 in the upper right tail, right? The table, sorry, not 0.1, 0.05. If I want 0.05 in the upper right tail, what area is going to be to the left? 0.95, which is actually the value I need to look up, right? Because the table kind of always gives me the area to the left. So scroll down here, 0.9, looks like it's in between these two values, so 1.64 and 1.65, so positive 1.65 or 1.645. So how could I get it out to the third decimal? Just kind of a review. If I wanted to go out to the third decimal, and I'm not using Excel, with Excel I can go out to whatever decimal I want. Remember, I want 0.05 in that tail. The very last row of the t-table kind of gives me those standard normal distribution values. So 1.645, okay? Any questions on that before we keep moving? All right, so we've got our critical value. What would this test statistic be? I mean, finding a test statistic, once we know the equation that we're using, right, it's just a matter of plugging in our values. There's not much, additional kind of instruction I can give at that point. Once we have more types of examples, I can give some more instruction about how we select which equation is correct. But, like today, I've given you the test statistic equation. It's really just a matter of plugging those values in. We get a test statistic of 4.9. So if I'm thinking here, my critical value is 1.645. My test statistic was 4.9. So am I going to reject the null or not? I'm clearly in that rejection region, right? So yes, for sure, with 95% certainty, I'm going to be rejecting the null here. Okay? Now, if instead I'd want to do the p-value approach, and this is why, critical value approach is fine. It's great. It leads you to the rejection decision at the alpha you want. But the p-value is really what the more useful part of hypothesis testing is. Because if I think about here, if I wanted to look up the p-value for 4.9, right? So that would be the area that is to the right of my test statistic of 4.9. Well, if I go to the table, right, and I try to look up 4.9, what's going to happen? Well, the highest value is 3.99. The area to the left of 3.99 is essentially 1, which means the area to the right is essentially what? 0. So that's the area to the left, to the right of 3.9. So the area to the right of 4.9 is going to be even closer to 0, right? So we essentially have this p-value that's approximately 0, which, if I only reject, if that p-value is less than alpha, well, once I find the p-value, I can tell you I can reject it at the 90% level, the 99, the 95, hell, the 99.9% level with this p-value, right? So it allows me to just make these really quick, I can tell you all the levels I could reject at very quickly, right? And especially if I find a p-value of approximately 0, this is telling me that, look, if what I assumed to be true was in fact true, that difference was 0, the probability that I found the sample evidence that I did is essentially 0. There's no way I found the sample evidence that I did if that in fact was the true value. So it's most likely that so I reject that, and it's most likely that what I assumed wasn't true. Right? The true difference is something much larger than 0, probably. Right? Okay. I feel like I just got kind of excited about that for some reason. We'll do, so that kind of covers that. I didn't have a slide for that, but kind of, the discussion of the p-value, it is important that, really is a little bit more useful than the critical values. So we can do the same thing for proportions, but I'm going to hold off on that for today. I want to just kind of show you this Excel assignment, kind of go over it for the next 4 minutes or so. So this is 2 population HT blank, right? So I've got this set up. Let me see which one. I think there's a couple extra sheets in here that we might not need, but that's okay. So we could do confidence intervals for the differences. We could do hypothesis testing. So I think, just because for the sake of time, I'm probably not going to get a whole lot of time to work through this. I just want to show you one thing in Excel so we don't have to waste time on it next class. So here's this sheet, which has the female BMI data on it. I have found the mean variance and the sample size. Hopefully we're getting really familiar how we do that with the data set. We've done this several times, right? Equals average, equals var.s, and the count function. Right? Then on this male kind of data sheet, right, what I've done is, right, I found the average, variance, and sample size for male BMI. Well, I wanted to put the values from the other sheet right here so I could deal with everything all at the same time. So you can do that if I get rid of this. If I put an equal sign and then I change the sheet that I'm looking at, I can still click on a cell. Now when I hit enter, it kind of puts this little thing at the beginning that says basically stay in this workbook, but go to worksheet female data and grab the value from cell L2, right? So you can cross-reference across different worksheets, which is a really nice way to kind of keep some of your data separate, right? Especially when I'm thinking about like height data or something, I might want to keep my male and female data separate there. If I'm interested in the difference between these two groups, I can quickly calculate some of the statistics I need on this worksheet and just reference them so that I can use them to build things like confidence intervals or hypothesis testing over here. Okay? So I wanted to mention that, and then we'll kind of start next class with this example. Apparently I didn't delete this one, so I'll delete these and upload the blank file again so that all this will be blank, and we'll kind of work on it together. Starting on Friday, we'll also kind of then begin the discussion of how do we look at the differences between population proportions, okay? All right, once again, if you had any questions over the exam, feel free to reach out to me. I'll try to get those graded at some point either today, definitely by tomorrow, okay? All right, I will see you guys on. Oh, and I'll get those two assignments posted as well. And I'll put up an online quiz after today's class that'll be due before Friday, okay? All right, we'll see you guys on Friday.